Hello and welcome back. Today we will talk about our first lesson, and it will be about the basic properties of complex numbers. So, first things first, let's introduce the complex numbers. Okay, so to begin with, we have the imaginary unit. We define an imaginary unit I, which is a number such that its squared is -1. And similarly, whether you choose I to define it, or you can choose the negative number, the negative value. And they are technically equivalent. And due to this, we will introduce the operation which is taking a conjugate of a complex number. But we will talk about it when we get there. And now let's introduce the field of complex numbers. I decided to introduce it as the set of all numbers that have a real part and an imaginary part, that are both from real numbers. And let us introduce the Argand diagram, and then we will talk about different forms of complex numbers. So, the Argand diagram. Basically, we can visualize any complex number on the Argand diagram, and we can write it as vectors. So we have the real axis and an imaginary axis. And in here we will have the real part of our number, A, let it be, and here we will have the B, the imaginary part. And just like that, we can write a vector which will correspond to our complex number Z. And if you remember the polar coordinates from real numbers, you may remember that we can also define this number in polar form, which will basically have the phi the angle to the real axis, to the positive real axis. And it will also have the r, which is also the modulus of our complex number, its absolute value. So, before speaking about different forms of complex numbers, let us define a complex exponential. So we define this will be our definition of a complex exponential. We will look at its properties later, and we will also explore how it corresponds to the real exponential. And we will find out that they are actually secretly the same. But that is for later. For now, let's talk about different forms of complex numbers. The first one is algebraic, and basically it is the one that I introduced in the definition. So we write a complex number z as a plus bi, where a is defined as the real part of z, and b is similarly the imaginary part of z. And both of them are real numbers. In terms of the angle and modulus, we have the polar form. It needs to be lower. Okay. The polar form. And basically in this form, a complex number z can be expressed as its absolute value multiplied by the things that we wrote there. Cosine of phi plus I sine of phi. And of course from this, by definition, we can get the exponential form, which is z is equal to r times e to the I phi. Let's first talk about the polar form. Basically it is very similar to the real analysis and polar coordinates. The r multiplied by cosine of phi is the x value in polar coordinates, and r multiplied by sine of phi is the y value. And basically, as we introduced the complex vectors on the Argand diagram, it is for all intents and purposes the same thing. And exponential is just a neater way to write it. So, in here, let me go back to yellow. In here, r is equal to absolute value of z, and it is bigger or equal than 0. And we also have the argument of z. And let us talk about the argument of z, because as you may have guessed, we can go 2 pi more radians and reduce and return to the same value. And so we have a multi-valued argument. I will write it in my notes with non-capital letter as the first one. So we define the multi-valued argument as its principal value, which we will define as also argument. It will be a principal argument, and we will write it as argument with capital A. And plus 2 pi k because of the periodicity, basically, of our angles. So those are our forms, and now let's explore how we can go from one to another. And similarly, as I have already mentioned, the real coordinate is equal to r times cosine of phi, and the imaginary is r times sine of phi. And how do we go back? If we take each of these values, we square them and add, then cosine squared plus sine squared is by the fundamental theorem of trigonometry, the sine and cosine will cancel out, and we will just get r squared. And after taking the square root, we will get r. So r is equal to square root of a squared plus b squared. In terms of phi, it is a little bit more difficult. You see, a simple arctangent, of course we will take a quotient of them, and then the r will cancel out, and we will get a tangent or cotangent. But the problem is that both of them are pi periodic, but we need our angle to be 2 pi periodic, because z and negative z are not the same number, and the arctangent will give the same value, basically. And that is why we have a special function for this. It is written as an 8 and a 2, of y and x, or in our case of b and a. And that is how you go from the polar form to algebraic. Next thing that I would like to tell you is that the set of complex numbers is indeed a field. So let's quickly prove it. This will be how we define our operations of addition and multiplication for complex numbers. Since we have already written the bijections between the polar and algebraic coordinates, I decided to introduce the multiplication in terms of polar coordinates. So let's prove it. Okay, let us have a look. At first we prove associativity, and basically how almost any property here is proven. It is through the use of either real and imaginary part, and then we, for those, use the properties of our real addition and multiplication. And for multiplication we use the properties yet again, but for the absolute value and for the argument of our complex numbers. The commutativity is proven in the same way. As identities, I have shown them, but basically, yeah, for them you would need to prove using our bijections the algebraic form of multiplication. And interestingly enough, for the zero complex number, the argument is not defined. Now the inverses are defined similarly, and distributivity is used by expanding using the algebraic form of multiplication. And then we show that they are the same, aka the real part and the imaginary. Now let's dive into the properties of our complex numbers. Finally, right? Okay. First, we'll talk about the modulus of a complex number. And let's show. Well, it can be directly proven from the definition, because we defined it in the polar form. So the absolute value of a multiplication of complex numbers is the multiplication of their respective absolute value. So, yeah. The second property is the absolute value of a quotient of complex numbers. So the 1 over the 2 okay, and how we prove this? Then we basically write as 1 over the 2 by definition as 1 multiplied by 1 over the 2. Then using the first property, we split those. And now we need to prove the absolute value of 1 over the 2 is equal to 1 over the absolute value of the 2. And how we do this, we notice that 1 is equal to the absolute value of 1, which is the absolute value of the 2 over the 2. Right. And using the first property, we will basically yet again split them. So it is the absolute value of the 2 by the 1 over the 2. And now by bringing the 2 to the other side, we get what we needed. Okay, the third property is the absolute value of z to the power of b is the absolute value of z to the power of b. Okay, for all b star real numbers, and I will prove it later. I will prove it simultaneously to the argument property that is also respective. Now we define finally the complex conjugate. So the complex conjugate z bar is defined as a minus bi for z that is equal to a plus bi. And if you look at the Argand diagram, if we mark the value of negative b here, and it again take the value of the conjugate, then we can also understand that it has the same absolute value, but the argument is negative 5. And this is particularly because we decided to make the branch cut of the argument as the negative side of real line. It is a very nice property. So that conjugate is also r times e to the negative i5. Okay, and this was a small side note that was not connected to the third property, but it allows us to define the fourth property, which is z multiplied by z bar is equal to the absolute value of z squared. And it is quite easy to prove in the exponential form. Write z times z bar is equal to r times e to the i5 terms are e to the negative phi, where r is the absolute value and phi is the argument of our complex number. And by definition of multiplication, these two cancel out, and we are left with r squared, which is also the absolute value of z squared, just like that. And now we will look at the properties of arguments. So, here we may have some problems, because you see, as we defined the principal value of our argument, it is actually from negative pi to pi, and it may be quite difficult to express that in our properties, which is why I will talk about the general argument. And the first property is the argument of multiplication is the addition of arguments. It is quite easy to get from exponential forms, because an argument of this is all pretty much by definition, and let's rewrite this integer as a k1 plus k2 that are both also integers. Then we can write it as phi1 plus 2 pi k1 plus phi2 plus 2 pi k2, which are basically the argument of z1 plus argument of z2. Isn't this incredible? The second property is the argument of a fraction, and as you could have guessed, it is basically the subtraction of arguments. The way to prove this is essentially the same. We rewrite this as an argument of z1 multiplied by 1 over z2. By using the first property, it is argument of z1 multiplied plus argument of 1 over z2. Now, hopefully that's alright. And now, we just need to prove that the argument of 1 over z2 is negative argument of z2. And how do we do this? Basically in the same way. So 0 is the argument of 1, is the argument of z2 multiplied by 1 over z2, and from here, using the first property, we split them as argument of z2 plus argument of 1 over z2. Holy moly, I'm so tired. Okay. And then again, we take this to the other part, and we get that argument of 1 over z2 is equal to negative argument of z2, and this proves the property. Now, we will consider the value of z to the power of b, where b is a real number. We define for that a complex logarithm. So the log z is equal to, it is basically such a value such that z is equal to e to the power of log z. And then we define this in z to the power of b is basically e to the b times log z. Now, how can we express the log z? We can actually express it as the real logarithm of absolute value of z plus the argument of z or basically ln of absolute value of z plus principal argument of z plus 2 pi ki. I forgot an I. Hopefully that is also okay. Now, we also have the principal value of logarithm defined, and it is yet again a real logarithm of absolute value of z plus I multiplied by the principal argument of z. Okay, let's write down a lemma. That is e to the power of omega 1 plus omega 2, that are both complex numbers, can be expressed as e to the power a1 plus a2 multiplied by e to the I b1 plus b2. How do we prove it? We basically take the value of logarithm of z. Okay, this is a proof, and for all omega j, say that is equal to aj plus bji, that are from complex numbers. Let's take a look at the log z. Of course, it is omega 1 plus omega 2, and by expressing them as real and imaginary parts, it is a1 plus a2 plus b1 plus b2i. And take note that b1 plus b2 we have with them loop around, so that they have the value from negative pi to pi. And because I'm too tired to take a look at the general logarithm. By looping them around, we take, we remember this and this. And from that, we can see that a1 plus a2 is the natural logarithm of e to the a1 plus a2. Does that make sense? And hence, the absolute value of z is e to the a1 plus a2. And similarly, b1 plus b2 will be the argument. Of that. And therefore, that can be expressed as e to the power a1 plus a2 multiplied by e to the power I b1 plus b2. And this is the exponential form of that. And basically that is what we needed to prove. So the lemma is proven. And what do we get from this lemma? If you look at z to the power of n, it is e to the power of n log z, and e to the power of n absolute value of logarithm of absolute value of z plus let's say the principal argument of z, and then we distribute because they are both pretty much real, except I forgot the I, but we have already proven the distributive property, so it is e to the power of n log z log absolute value of z plus I n argument of z. And what do we get from here? From that, so we get that the logarithm complex, let's say the principal one. I think it is easier to do with the general one, but I want to do it with the principal one. So the log z is equal to n ln z plus I an argument of z. Hence, the absolute value of z to the power of n, of course, is and we can rewrite it as the natural logarithm of absolute value of z to the n, and let's take another absolute value because we can, plus I n arc z. Okay, and from here it is from this form we can get that this the absolute value of z to the power of n, and the argument of z to the power of n is equal to n multiplied by the argument of z, but take note that it needs to be looped around, so it is from negative pi to pi. And here we have proven the third property, or I think it was the third one, of our absolute values. And we have proven also the property of arguments, which is the same. So the third property is argument of z to the power of n is equal to n times the argument of z. Of course, we can just add plus 2 pi n, and basically it is this. So the proof is already shown. And now let's move on to the fourth property, which is the argument of z conjugate is negative argument of z. And basically we have also already proven it geometrically by construction. So proof already shown. Okay, and now let's move on to the final topic for today. Finally, it is the Moivre theorem. It says that cosine theta plus I sine theta to the power of n is equal to cosine of n theta plus I sine of n theta. And theta is a real number, and you may have noticed that it is basically another form for this one that we have thankfully already proven. So we have already proven it, but also let's have some fun and prove it for natural n by induction. So the base of induction will be n is equal to 1, so cosine of theta plus I sine of theta to the power of 1 is indeed equal to cosine of 1 theta plus I sine of 1 theta. Yay! Then we have the thing that we need to suppose for our induction, and let's just say that it holds for n. Which is a natural number. So basically, cosine theta plus I sine theta to the power of n is equal to cosine and theta plus I sine and theta. Holy moly. And now we do the step of induction. We take, let's write it as cosine of n plus 1 theta plus I sine of n plus 1 theta is equal to, by writing the cosine of some formula, we get cosine of n theta plus multiplied by cosine theta negative minus sine of n theta multiplied by sine of theta plus I multiplied by sine of n theta multiplied by cosine of theta and plus sine of theta by cosine of n theta. And then by taking out the let's take some beautiful color cosine theta here and here, and let's also take out the sine theta here and here, because we have already proven the distributive property, and we will have the cosine theta multiplied by cosine of n theta plus I sine of n theta, and the same will be for sine of theta. I could even copy it. Can you imagine that? So we copy, we paste it, because that is the same. Okay. By using the distributive property, we can take these two out, and by using the things that we supposed, this one are basically to the power of n. So it is cosine theta plus I forgot, I sine theta, and multiplied by cosine theta plus I sine theta to the power of n. And basically, isn't this incredible? It is the cosine theta plus I sine of theta to the power of n plus 1, which is what we need to prove. How absurd is that? And this is basically it for today. The lesson turned out to be a bit longer than I expected. For whatever reason, I expected it to be a 10-minute lesson, but whatever. The point is, we have done everything that we needed to do, and we can be happy. And if you notice a discrepancy with the introduction of complex logarithm, please do not pay attention to it. It was my bad. I kind of failed to find a reasonable way to prove it, but I think that it was correct. It should be. Because by intimidation. And I see you on the next lesson, where we will talk about domains and topological terms in complex numbers that we will later use to define stuff like analytic functions of on I am also a little bit sick, so sorry for that, and a little bit silly, and sorry for that too. Thank you for your attention, and goodbye. Haha. If you thought the video was over, you were wrong, because we have a bonus. And fun fact, I thought that I was recording with my headphones, but as it turns out, not, because Samsung is so horrible. And now I checked, and the headphones actually sound much worse than the audio recorded like this, like you currently hear. But back to the topic. Let's apply the Moivre's theorem. So, application. This is from the basic Moivre's theorem. But now we can expand it using the binomial formula, and we will get the formulas for the cosine of n theta and sine of n theta. By taking the real and imaginary parts. Okay, so it will be a sum. And just okay. Just like that. And we can also write the formula for the sine of n theta. And it is pretty much the same, except we have a 2k plus 1 instead of 2k, because we don't have the even terms, but we have the odd terms. Why? Because we need the I, the imaginary unit here, to be the correspondent to this one I. Okay? And this was also okay. And that is it for this one topic. But actually, I have also brought you some visualizations. So, you see, we can use Desmos, the graphing calculator, in order to visualize all the stuff. For example, here is the definition of our complex number, and its different forms. And as you can see, they are one and the same. Because in formulas they are one and the same. Oh no. Okay, we also have the visualization for the Argand diagram. And as you can see, you can drag around this point. You'll see the imaginary part, the real part, and the argument, and the absolute value. So, isn't it very nice? We also have the properties of complex numbers. You can also drag around these points, and basically we show that the different forms of them that are supported by the properties are indeed their respective values. And keep in mind that in the formulas I neglected the negative pi to pi restriction on the principal argument, because when computing they just loop around automatically and it doesn't make a difference. And in the end, I would like to talk to you about the roots of unity. Oh, that is quite horrible. Well, whatever. Oh, it's better. So, as you may have remembered when we wrote the properties of the argument, uh, in particular, z to the power of n, then the plus 2 pi k part of the argument also gets multiplied. But when we have an integer power, when we have an integer power, then we will have an even more multi-valued solution. And in this case, the multi-valued solution will correspond to different numbers. Not only different arguments, but also different numbers. And they are called the principal values of our root, aka the roots of unity. In this visualization, you can change the power, and if you can see, as you can see, for z that is equal to 1, they actually form the right n-gons. So for example, the right hexagon, the right triangle here, or a square. And we can also drag around this point of z and see how they change. Isn't that absolutely incredible? Okay, and at this point, I would also like to mention another thing, because you see, when we have, oh no, when we have an irrational power, then it also gets affected. I mean, the argument and the plus 2 pi k part. But instead of just looping around, as it did with the previous example, so you can see that it loops around and then it goes back. But instead of looping around, it will just go on changing the values. And in here I actually have 100 of the values. And it's quite nice, isn't it? And in data there will be an infinite number of them. So keep that in mind. And for now that is all for me. Thank you for your attention and see you in the next video. Bye bye.